That should be enough time to let people trickle in. There's a few things I want to go over before I start with the actual material. I made some changes to the syllabus. Did everyone see that? Okay. Brief summary of changes off the top of my head. The final now has a date. It's going to be on the last class. There's a few changes that I made to the weightage of things. Attendance is and participation is now going to be 10%. And part of the reason for doing that is the final, since it's going to be in class, it's an hour, 20 minutes long. So making the final 30% isn't something that would make sense. And this is something that I was advised to do by my mentor. Um, that was one change. The other thing that I didn't have in the syllabus earlier was that out of the total 5 quizzes, I'll be considering the 4 best ones. So if you miss a class, because quizzes are going to be in class only, that they're usually only 15 minutes long, which is something I didn't know going into this initially. That's how it used to be done. So yeah, if you miss a class, it's a 12-week semester. If you assume there's going to be one quiz every 2 weeks, then the odds of you missing a quiz, if you skip, say, 2 classes, is pretty low. Um, that was changes in the syllabus. There's something else that I was recommended I should go over, considering this is something that Dr. Rata had gone over in his class last year, and despite that, it was a larger class, but he had a handful of cases who had violations, and he had to report them. And the thing is, once a violation gets reported, it's out of the faculty's hands, more or less. The Office of Academic Integrity decides what to do. So this um, it it covers a few, I'd say, examples of um, gotchas that may not be immediately obvious if you're new to UB, or if this is your first semester, which I don't think it would be, but regardless. Um, if it feels like cheating, it probably is. That's a general rule of thumb. If you're not sure, ask. Uh, Self-plagiarism is one of the things that is also not immediately obvious. If there's something that you worked on before for a different class, you can't use it here, because whatever the expectation is that everything you do for the class, whether it's homework or the project, is from scratch. Um, Cheating, contract cheating. I Getting someone else to do the work. Yeah. You guys, um, a lot of these things, like just from the keywords, it's not immediately obvious to me, because these aren't things that I've ever had to think about necessarily. Just I get homework, I do it. That's all there is to it. Don't get anyone else to do your stuff for you. Don't try to mess up anyone else's work. Um, ChatGPT, yeah. This is, we all use it, but for quizzes, since they're in class, are going to be using lockdown browsers, so that there's no way you're going to be able to switch out tabs, look stuff up. For code, it's a bit trickier. There's no reliable way to catch it. There's a few startups or tools who are trying to say that they are able to detect it, but it's still not very reliable. just err on the side of caution. It's really not worth it. Like you could get a C or a D in the class, but that still wouldn't look as bad as having a violation on your record. Processing it, yeah, this is more for me than for you guys. That what I'm supposed to do. In case I find something, I'm required to report it. I've already linked to a lot of the policies in the syllabus, so make sure you're familiar with them. I will be running MOS on all code, and I've been writing code long enough that I'd say I'm reasonably good at telling when there's like inconsistencies in style, and that's only I'm going to be able to do that better the longer into the course we are, because I'll have seen more of your submissions by then. Yeah, first offense, you get an F directly. And this is the CSE department's policy, not the broad UB policy. So the interplay of both of those will be decided by the Office of Academic Integrity. Groups are the only exception to being able to work together and discuss stuff, but in groups, if it turns out that your submission looks off, then regardless of whose fault that is, everyone gets penalized equally. It, oh, this is especially relevant for the project. So you are allowed to use code off of GitHub if you find a paper that has a repository that goes along with it, and that's what you want to use as your starting point, and you will be introducing novelty into that. You still, whatever you use, you have to cite. And for homeworks, the format will be a problem definition in a PDF, and that will tell you what libraries you can and can't use, what functionality you are allowed to use. So just stick to those, and you'll be fine. This improper distribution, I mean, I intend to make everything public later, so I didn't put this notice in my slides. Collaboration, yeah, the accommodations. Okay, yeah, I already went over all of this stuff, so I'm gonna start with the actual course material for today. This is something that I'll pull up later today. Okay. Time to get into the actual material. How's everyone feeling today? Ready for some math? There's going to be a few initial slides that are kind of dry. I've tried to make them as visual as possible because that's how I learn. And once that's out of the way, we'll have a lot more fun. So today we're going to talk about image formation. From the book, few parts of the process. There's perspective projection, which is taking your real world scene and mapping it to a 2D plane, which we'll be talking about in some detail today. There's also light interactions with surfaces, a little bit of the optics aspect of how images get deformed based on what lenses you're using. And D is a Bayer color filter array, which I will also be talking about today. So big stuff ahead. To be able to understand all of this material, we need to have a vocabulary that is consistent across the field. These are called the geometric primitives that we'll be using a lot throughout the entirety of the course. We have points, lines, planes. And after that, once we define all of those, we'll look at transformations that remap geometry. So Does anyone want to break the ice? Tell me what a point is in an image. Just throw words out. We know that an image is a 2D array of what? Yeah, pixels. Good. Um, so how do you locate a pixel? You need to be able to have an address for a pixel. Um, the coordinate plane convention varies slightly depending on what framework you're working with, what software you're working with. Usually you'll find that the origin is at the top left corner. So you call this a fourth quadrant plane. Um, the order in which you index also varies from framework to framework. So some of them do row first, some do column first. Um, it it doesn't really matter, but basically you need to know how far along the x and y axes a pixel is, and then using those two values, you're able to select a pixel. Um, so that was represented as a column vector. Now, you're able to augment this by adding an extra row to it, uh, which is just a 1. And when you're talking about it in terms of which axis it represents, you would call it the x. You already have the x and y, and then there's a w term that's added. And what this does is the w term lets you sort of represent the depth of the plane at which you're projecting the 3D object. So when it's 1, it's basically 1 focal length away. And I'll come back to this a little bit once I show the image formation visuals. Um, Points at infinity is a special case. So if you set it to 0, that usually lets you talk about only direction without distance, and that becomes useful later when you try to do uh, projections. So converting from Cartesian to homogeneous, you just add an extra row to the column vector, and they can be converted back and forth. And the cool thing about this is what it lets you do is you can multiply the entire vector by a constant, and those coordinates will be equivalent. So a 2, 4, 2 and a 1, 2, 1 represent the same point of 1, 2, but you see that it's it's essentially a plane that's 2 focal lengths away and larger. So from there, we talk about lines. Now, the 2D Cartesian line equation can be represented using as ax plus by plus c, where the coefficients are a, b, c, and to convert this to homogeneous, you just add a w. So over here, that's an implicit 1. So if you want to represent an equivalent line on a plane farther away, you would change your w value. Now that we know how to represent a line, um, when we're trying to do vector operations with it, you would only take the coefficients of those. So does anyone have a guess on what a cross product of this would do? You have two vectors for two lines and coefficients of those. So it's some sort of an interaction between lines. How would lines interact? Yeah, close. So perpendicular is talking about the angle between them. To form an angle, what do two lines need to do? Intersect. So taking the cross product of two lines gives you the point at which they intersect. And similarly, if you take the cross product of 2 points, you get the line joining them. And I have a little example for this. So far, I've just been talking about coefficients and vectors and stuff. So I think this should help solidify that a little bit. Okay, it's up there. So we start with a line that has the equation 2x plus 3y plus 4 equals 0. And converting that to a vector representation, you take only the coefficients. That gives you 2, 3, 4. And this is a row vector. And for points, we do column vectors. So the point with coordinates 1 and -2 in homogeneous form becomes 1, -2, 1. And dot product of a line and a point gives you, lets you check whether they intersect or not. So once you take the dot product, that's 2 times 1, 3 times -2, 4 times 1, and you add them all together, that adds up to 0. So that means that the point is on the line. And to find where they intersect, we take another line that has the coefficients 1, -1, and 1, and the line from before, that was 2, 3, 4, and we look at their cross product. So one thing, you take ijk, which are unit vectors, and calculate the cross product, which is done by taking the determinant of each sub matrix 2 by 2 first. So for I, you would look at 3, 1, -1, and 4. And when you're doing that for j, you add a negative sign and do the same thing for 2, 4, 1, 1. And similarly for k. And then when you add all of that together, what you end up with is 7, 2, and -5. So this is in homogeneous form. So to convert to actual Cartesian coordinates, you would, this is the w term, you would divide the x and y terms by the w term, which gives you -1.4 and -0.4. And I've put this up on UVLearns also, so feel free to go over it again if you would like to. I hope that helps put everything a little bit more into context, since we were just talking about vectors and coefficients and stuff. Okay, from there. So far we've introduced lines and points. From there, we go to planes. There's not a whole lot of manipulation of planes that we'll be doing just yet, but a plane is a slice of a volume, essentially. And it can be represented by adding a z term to it with its own coefficient. And it can also be described using a normal vector, which is a vector that's perpendicular to the plane and passes through the origin. There's polar coordinates, which we won't get into right now, but once it comes up, we'll use it when it's relevant. So since this is still the second class, let's talk about how an image is actually formed. So last class, I mentioned that an image, a scene in the real world, gets formed on the retina. It passes through the lens in our eyes. It's pretty similar for what goes on in a camera, whether it's a pinhole camera or a digital camera. So when you want to form a real image, you would use a convex lens, and what that does is it inverts the image of the object. So analyzing the eye or lenses, cameras is usually done using the pinhole camera model because they're functionally equivalent. We work with a virtual image since we don't want to deal with the inverted one. Basically, whatever the focal length is from the pinhole back to the screen on which the image is formed is the same. We can project that forward one focal length away, so they're of the same scale, and that also takes care of the inversion. It's an assumption that we're making. So think of the back of the box as where the sensor would be. To assign values to pixel coordinates, we use the virtual image plane as our reference, the homogeneous coordinates that we talked about, and the projection plane is where the image would be formed and the one whose coordinates and properties we're interested in. So things that should pop out from here is that you have the object at some distance, and then we have our virtual image, and the scale is different. So if you're looking at a picture of something versus the actual thing, they're not of the same size. So to preserve the relative relationship between all the points that you could sample on the actual object out there, we record incident light intensities at each point on the plane. And that maps to a grid. So we already know that we are able to capture light intensity. So dark and bright, we know how to represent that in 2D. What about color? Does anyone have any ideas how we would represent color? There's a little hint there. Yeah, what do you do with RGB? Or why RGB rather? What's so special about those colors? Because they are primary colors. So we take red, green, and blue. Since they're primary colors, we're able to mix and match them to get whatever actual color we want to represent. Combining red, green, and blue together with full intensity of 255 if we're working with 8-bit values means we have white since all of them are at their maximum. And if you set all of them to 0, you get black since there's no color whatsoever. The way this is recorded is cameras usually have CMOS sensors that record light intensities, and there's a filter which is called the Bayer filter that sits in front of the sensor. And the filter lets in only light of each primary color at certain regions. So the regions that correspond to a filter that only lets red through would record red values, and similarly for green and blue. Now, how do we put this together? For grayscale, which is just intensities, we know that it's a 2D array. But we now have red, green, and blue, and we need to be able to put all of those together. So color images, even though they're flat 2D images, the way you store them is as a 3D array, a 3D tensor. Um, we don't typically call those images 3D because when we say 3D, we're talking about depth in the real world. So uh, even though the arrays have a third dimension, we still talk about them as flat 2D images. This also crops up a lot when you're trying to do filtering and stuff with it later on, which is why you'll see that one of the first steps when dealing with images, color images, is you would typically convert them to grayscale. Combining the three of them, you get a full color image that also encodes brightness. But this isn't the only way to do it. I'll, okay, I went on a tangent a little bit. That's for later. I whipped together a little example in code just so it all feels more real and tangible. This is typically how you would start off all your assignments, with the exception of using this color space conversion. That's something that you're not going to be allowed to do. Um, so we start by reading the image. This is done using OpenCV, which is what the import CV2 is. OpenCV has this quirk, or they made a design choice when they were building the library, which is that they would read images in BGR format instead of RGB, like all the other libraries do. So you have to reverse the order of the channels, basically. And once you do that, you can plot it in Matplotlib. So this I did in a Jupyter notebook. Is everyone familiar with doing Python programming? Uh, okay. So you see here that there's, when I look at the dimensions of the image array, there's 3 values. And the third one is the count, channel count. So this corresponds to red, green, and blue. And the first two are height and width. And how you would look at the individual channels is using indexing. So the colons there are to just select all values basically for those axes, and then 0, 1, and 2 are selecting each channel individually. And so the borders here are entirely red. So when you look at the red channel image, those show up as really bright because there's a lot of red, but that there's nothing in that region in the green and blue channels. But if you look at the arrows and stuff, those are white. So there's all 3 colors, and that means the intensities for those are high regardless of what channel you look at. How you would use the coordinate system that we talked about initially to address a pixel. You Slicing is how you select a sub-region from the image. So I selected height from 800 to 1200 and width from 600 to 900 and plotted that. So those are pixel coordinates. And since I didn't specify a third value, it returns red, green, and blue, all of them together. So the RGB color space is one way to represent the image. There are many others. This one that I have up here is called HSV, which stands for hue, saturation, and value. How does this differ from RGB? You have all the color information in the hue channel. You have how intense that color is in the saturation channel, and then you have brightness information in the value channel. Any guesses on what this would be good for? Or um, what is something that you cannot do with RGB that you'd be able to do with HSV? If I wanted to find regions of a certain color in an image, which one do you think would make it easier for me? There's only two options, come on. I heard an HSV over there. It's RGB. You can look for stuff using colors, but it's a bit trickier. So in HSV, since all of your color information is in one channel, it doesn't depend on the other channels. So to find something that's red is you only have to deal with one channel and look for a certain value there. In RGB, if you have a region in red that has more light on it that's brighter, then when you look at the actual the color value, it will be different since light and dark is achieved by adding more green and blue or removing green and blue to make it darker. So there's that interplay between color and brightness in RGB that HSV gets rid of. And you can see that with this example. So here I've set green and blue to 0, and I'm looking for all reds. And what I'm doing is I'm selecting every pixel that's within the lower color and upper color bounds and creating a mask. And there's not much in that mask that matches the requirements. And now you would expect a lot more since there's a whole lot of red in the image, but it doesn't show up because of the brightness varying. So it's not a pure red, basically. The same thing when I try to do it in HSV. So there's two ranges for red color. I should have put in an image. So the way hue works is it's a wheel uh, that just keeps cycling through all of the colors that you can think of, basically. And I've selected the range of reds in the hue color wheel, which goes from 0 to 10 and 170 to 180. And then I did the exact same thing, made a mask, and this time I got all the reds. So we know about how to represent color images also. Now we talk about transforms. Yeah. Yes, if you're using, you can store them as 8-bit integers. Uh, the value range, I'm not certain about it. LAB, I haven't worked with. HSV, off the top of my head, I think that it's 0 to 255 for all channels, but I will check and get back to you. That's a good question. Let's write that down somewhere. Okay. Uh, Transforms. Transforms is the things you do to an image, uh, loosely. So translation is when you're moving it. Uh, Projective is when you're uh, reprojecting it to a different plane. Affine is when you're warping it. Euclidean and similarity are combinations of linear transforms that we will go into. So linear transforms, there's four that we can do. There's scaling, which is making an image bigger or smaller. You can either do that along one axis or both. Rotation is rotating an image around the origin. Um, if you don't want to do it around the origin, that comes later. Flipping or mirroring it is either around the x or y axes. You take the farthest away pixels and put them farthest away on the other side, closest ones on the just around the axis. Shearing is when it's the name originates from shear stress in mechanics. When you apply a force to an object along the top, it deforms and a square becomes a parallelogram. So some properties for a transformation to be linear is that the origin should be preserved and lines will remain lines, parallel lines remain parallel. Um, Ratios of features in the image will be preserved so that things don't get bigger or smaller relative to each other. And closed under composition. Closed under composition means that when you have a bunch of linear transforms that you apply to an image successively, um, putting all of them together, the end result is still a linear transformation. So you can combine all of them into a single operation and it will be linear. So an example of scaling, there's simple matrices associated with each transform that you then apply to coordinates. So you would take the scaling matrix, which is a diagonal matrix, and k is the factor by which you want to scale along the x-axis in the first case. Um, if you want to do both along the x and y axis, you would just make the entire diagonal k and k. And to double it, that would be 2 and 2. And you take coordinates of each pixel and multiply it by this matrix, which gives you the new coordinates. And then you would take pixel values from the old location and plug it into the new one. And that gives you your rescaled image. So for stretching, we just, if you want to double it, you put in 2's over there. If you want to squeeze it, what do you do? Yeah, you would put a fraction, basically. And that will give you new coordinates. Rotation, as I said before, it has to be around the origin. So whatever angle you want to rotate by, you plug that angle into the matrix over there. Depending on whether you're trying to go clockwise or counterclockwise, the sign for the sign element changes. And this is defined for the fourth quadrant. So for fourth quadrant, the way that we typically work with, this will change, and that I leave up to you because that's you can expect that to be part of a homework. Flipping. We saw, what did we see so far? Scaling and rotation. Flipping. we know what two matrices look like for scale and rotation. Does anyone want to volunteer with a guess for what we're trying to do? What the matrices would look like? So your typical matrix, oh, no markers here. Typical matrix is along the diagonal, you have coefficients for what you want to multiply your x and y terms with. So you want your x to go to the other side, you would make it negative, right? Similarly for y, and this is what that would look like. So to take an existing x and get the new one that's flipped around the y-axis, you want all your x coordinates just to be their equivalent on the other side of the axis. So you just multiply it by -1, and you keep your y values the same since it's around the y-axis, so the image is still above the x-axis. And if you're flipping it diagonally, then you want to interchange the values. So these are the values you plug in. An example of shearing stress, which I meant, not stress, shearing transform that I mentioned earlier, which comes from shearing stress in mechanics, is applying a deformation to your image. You're basically moving all of your rows by a certain amount, and you take your shear value and plug that in here, and that gives you new coordinates for each pixel. This brings us to translation. Translation is you want your image to move. So you could simply just add whatever x and y offsets you want. Would you be able to represent that as a 2x2 matrix of linear transform? You're moving an image. Would it be a linear transform? Right. It doesn't preserve the origin. So how do you represent it then? We go back to our homogeneous coordinates for this. That makes representing translation really easy, piece of cake. You just retain the original scale and add your offsets to the new column. And when you multiply this with your pixel coordinates, you get your translated coordinates. So since it doesn't preserve the origin, we do it in homogeneous coordinates. And the third column lets us account for the translation components. The other cool thing about using homogeneous coordinates is that all of the other 2x2 linear transforms that we looked at before, we can just plug those in here and combine the operations. So you can translate and rotate, or translate and shear together with these values and translate with those. So when you add the extra row at the end and a new column and do transforms using homogeneous coordinates, we call those affine transformations. All of the previous transforms we can represent as affine transformations also, just by adding an extra row and column and then getting the new coordinates using that. So another example, This one, it reuses the same image loading logic from the previous example. I'm extracting, unpacking the three dimension values into height, width, and channels. Is this clear enough? Can everyone read, or is it too small? Is it fine? Okay, cool. So this is the transformation matrix to stretch it along the x-axis. I plug in a k value of 2, so it should double in width once I do that. And since you need somewhere to copy the pixels from the original image to the resized one, we first create an empty one that has double the width, an empty array, and then go over each pixel coordinate, calculate the new coordinates used by applying this matrix to it over here, and that gives us the new x and y. And then we take the pixel values from the old non-transformed image and then plug them into where the new coordinates are. And what that gives us is this. So it's wider, but it's also darker. Any guesses on why it's darker? The operation that we're doing, unfortunate that I don't have a whiteboard. Oh, they're right here. That was, um, so we started off with iterating over each one. We look at this pixel, and then we have another one that's twice as wide. So if we're doubling along the x-axis, this value still goes over here. This value goes over here. But what happens in here? That there's nothing over there. So we were able to double the width, but we lost a lot of, or rather, we're missing a lot of information since there's empty pixels. And if this were a lower resolution image, it would show up a lot more clearly that there's gaps in it. But since it's at the resolution that it is, it just shows up as darker. So what I did is I replaced the values of all pixels that are empty with green, and this is what I get. So it's basically alternating an actual information pixel with an empty pixel that I'm highlighting in green, and that's where all the zeros are. How would you solve something like this just intuitively? If you have empty values, a bit louder, replicating the neighboring pixels. Yes, you could do that. So what would a downside of that be? Because if you're going from values that are like, say, 12, 36, 20, and you have a 12 here, you plug in another 12 here, then 36, 36. You, it's not going to scale. If you're trying to, instead of doubling it, if you go up to, say, 16 times, then you just have the same value 16 times, and that makes for a very blocky image, right? Because you'll see the same thing repeated, and we want smoother transitions. So, did you say something? Yes, averaging is a it's a reasonable, intuitive start to solving the problem. Interpolation is what that is called. Interpolation it's something that comes from signal processing. Um, when you sample a signal, you need to have a high enough sampling frequency to be able to capture the changes. And that's typically whatever the signal frequency is, you want to sample at least twice as much as that. So if you have, uh, actually, I'm not going to go into that, but interpolation is a bunch of strategies to deal with missing values. And one that we're going to look at now is called bilinear interpolation. There's a few others that will come up later. There, for now, I'll be touching on bilinear interpolation. So this case here, we have a point that's sitting in between four other pixels, and we need to assign a value to it. The example that I talked about before was fairly regular, so the new point that we have was spaced squarely in between these two pixels. So this one's right between there. But if I'm tripling instead of doubling, then I have one value that's closer to this one value that's closer to the other one. So irregular distances will definitely come up. And the way we deal with it is by looking at the values of the pixel at the opposite corner. So first we break it up into smaller rectangles. That gives us this. And for this rectangle, we look at the opposite corner, which is red, and we use that as our reference color. And then depending on how much area those rectangles take up in there, we calculate a weighted sum, which then finally gives us what the value for that pixel should be. That brings us to camera intrinsics. It's not a very smooth segue, I'll admit, but it's one of the last factors that we need to take into account when thinking about how an image is formed. So far we dealt with just the geometry of things out there in the world and how those end up on a screen. And there's one part we didn't talk about, which is the optics. So if you have, depending on what kind of lenses you have sitting in front of the sensor, that will affect your image. And there's four parameters that we care about to get as accurate of an image as possible. And they are focal length, principal point, pixel aspect ratio, and skew. So focal length is pretty intuitive. I think we're all familiar with what the focal length would be. It's how zoomed in or zoomed out the camera is. Shorter focal length will have a wider field of view, and then once you zoom in, you're tightening that up, and you have a narrower field of view. Principal point is where the optical axis intersects with the image plane, and this is usually the center of the sensor. It's pretty rare that you would have an image that is formed off center for a set of lenses and a sensor. Pixel aspect ratio is each element on the sensor array, how its edges are relative to each other, whether they're the same in height and width or not. Typically, they're all square, so we assume them to be 1-to-1. And the skew talks about non-orthogonality between the image axes. So if your x and y XYZ axes are not at 90 to each other, the skew parameter would come into play, but that's hardly ever the case, so we consider that 0. What do you do with all of these values once you have them? These are represented in a camera calibration matrix, and fx, fy are the focal lengths in x and y directions respectively, as skew parameter, and cx and cy are coordinates of the principal point. So this, you'll see that this has some similarity to the translation case that we looked at, which was moving the origin. I think that that should feel familiar. Once we have all of these, we can then take a point in 3D space that's out there and apply the camera intrinsic matrix to it, which then gives you the coordinates of where that point would end up on your plane. And yeah, that was all the material that I had for today. I'll be moving on to the next chapter next week. If there's any part that you guys want me to like go back to talk about a bit more, or if there's questions, I can take those. Okay, yeah, free to leave. Since we're done with all of this, you can expect homework soon. I will probably release them on Saturday. Just keep an eye out on, I'll post an announcement on Piazza when I do that. Yeah.
During deep learning course in the last semester, in the spring semester, I worked on the project of coloring the black and white images. And I used LAB channels to predict the like intensity from the black and white image.
Okay.
And using that predicted like A and B channels using the intensity. Then I predicted the superimpose the like A and B channels on the intensity and then created the color image.
Okay.
I tried the same using RGB channels, but the accuracy was far better with LAB channels than RGB. Even though the color in LAB depends on both A and B channels,
Okay.
and in RGB on 3 channels, LAB works better than RGB. Why is that?
LAB, I'm not very familiar with LAB. I haven't worked on it, so without looking into it, I can't answer that. But I'll read up on it.
I got this doubt because you told about the HSV channel like format. There, like just using one channel, we can predict the intensity of a color, right?
Yeah.
So in that case, like here, in both this one, multiple channels are required to like predict the to go through the color.
I can try to look at it now. Yeah.
The way LAB works is L is the luminance of the pixels,
Okay.
and A and B are the color channels. Like both channels representing two-way color.
Perceptual likeness in A and B for 4 unique. Oh, so this red, green, blue, yellow.
Yeah.
Yeah, so with RGB, the issue with identifying a color was that bright and dark shades um, are bound to color, right? So since luminance is capturing brightness, The other two channels are um, encoding only color. So for a combination of those two channels, one value, regardless of brightness, it's going to remain the same, right? Since your L channel is taking care of intensity independently.
And regardless whatever the values of L channel for that pixel from 0 to 100, L channel will always be same.
No, so okay, if I take a picture of this, then this region is darker than this, right? But the color is the same. The reason they show up as different in RGB is only because of the brightness, right? Now in HSV or in LAB, HSV color is addressed only by the H channel. LAB color is addressed by AB. Um, but once you know whatever the representation for this particular color is independent of light, you can represent that in H or AB, right?
Yeah.
And in HSV, brightness is with the V channel and LAB brightness is with the L channel. So brightness and color are now independent. So
Okay.
once you know color, you can just ignore variation in brightness, right?
Yeah. Okay, so for example, like if the light on the like just plain white image,
Yeah.
if the light is from this side, and so obviously this corner will have the brightest intensity, and this corner will have least intensity. So all the like across the images, A and B channels will be constant. Just L will be the variance.
Yes.
So that's how that will be easy.
Yes.
Okay.
So if you plot the L channel, you will see the gradient. If you
Yeah.
plot the
A and B
AB
is
channels,
just,
it will be flat.
Got it. Thank you.
Yeah, you're welcome. Uh, I am recording them. It's something that I was going to ask my mentor. I forgot about that. I'll ask him whether I can make them available. Recording channels. I'll get back to you about that. No, there'll be code and probably a report that goes with it.
I mean, with some calculations we can use iPad for that.
Homeworks will. So I'll tell you a couple. It'll be implementing some of the things that we talked about, like flipping, rotation, all of that. Yeah.
We talked about stretching them.
Yeah.
Where you just interpolate for the filling the empty bits.
Right.
So what about shrinking? Do we just take average of range of pixels?
Shrinking. So when you're shrinking it, you're going from a bigger array to a smaller one. So you won't end up with any empty pixels, but you'll have to do anti-aliasing for that, which will come up in a future class. So a very simple way, wait, let me put this up there. Anti-aliasing. This is basically what you end up with when you have like sharp transitions, right? So this has more to do with shape than like color or intensity, but the principle is the same. That when you go to a lower resolution, if you don't do any filtering or pre-processing with it, then you have sharp transitions. So a very rudimentary way to solve that is you first blur the image and then downsample it. So that makes sharp transitions a bit smoother. But anti-aliasing is what I believe you would have to do. I'll be able to explain it better once I go over that part of the material myself. Yeah, I think it should be part of the next topic. Next one is image processing. Right? Uh, yeah, it'll definitely come up. I don't know off the top of my head what all the topics are, since I am still like in the process of making slides. I was making them yesterday and today morning. I'm not using the older slides directly, and I'm pulling from a bunch of places. And it's definitely part of other slide decks from. I'm using University of Washington and Cornell as two of my main preferences that I'm pulling from. It's on there, but just everyone orders it differently.
Also for the grading, is it relative?
Uh, the that's another thing that I have to ask my mentor how he did it last year, like what the thresholds for each grade were. If the class average is above 85%, then whatever that scale is, I'll just follow that exactly. If class average is lower than 85, then I'll curve it up. I'm not going to curve it lower. So whatever people get, they will get at least that much, if not more.
When was the project? Uh, description of it?
Um, Maybe by the end of next week or early week 3, I'll try to put it out.